This is lesson 23, quantum numbers. So remember that orbitals have characteristic shapes and energies. Remember, orbitals are not the same thing as orbits. Orbitals are like rooms where electrons stay. An orbital is referred to the probability of finding an electron in that region. Quantum numbers describe an orbital. So the first type of quantum number is called the principal quantum number, which is n, and that tells you what energy level an electron is in. So remember, energy level is the same as period. The second quantum number is called the angular momentum quantum number, which is L, and L can be anywhere from 0 to n minus 1, and that tells you what shape it is. So if an electron is in an s orbital, its L is 0. If it's in a p orbital, its L is 1. If it's in a d orbital, its L is 2. And if it's in an f orbital, its L is 3. The magnetic quantum number, ML, can be between negative L and L, including 0, and it tells you the orientation of the orbital. So x, y, or z orientation. An electron shell is when you have all the orbitals with the same value of n, so all the orbitals in the same energy level. The total number of electrons in a shell, so like the first shell, is 2n squared, where n is the principal quantum number of the shell. A subshell is orbitals that have the same n and l values, so the same energy level and the same orbital type value. So orbitals that have energy level n equals 3 and l equals 2 are the third energy level, d, because L equals 2 orbitals. So subshells are designated by a number, n, and a letter, S, P, D, or F. So s orbitals are, remember, when L equals 0, they're symmetrical and they're spherical. And remember, for s, your ML quantum number is 0. So s orbitals again are spherical, okay? So this would be the 1s orbital, and then between the 1s and the 2s orbital, and then after the 2s is the 3s orbital. So your probability increases every time you enter one of the s orbitals. P orbitals, where L equals 1, are dumbbell shaped, okay? And starting with n equals 2, each shell has 3 different types of p orbitals. So there's 3 2p orbitals, there's 3 3p orbitals, and so on. ML can be -1, 0, or +1. So here, for example, are 3p orbitals. So here this would be -1, 0, and +1. Tells you which one they're in. D orbitals are when L equals 2. And remember, there's only 3d and above, so you can't have a 2d or a 1d. And d orbitals are clover shaped, except for this exception right here. And there's 5 3d orbitals, 5 4d orbitals, so 1, 2, 3, 4, 5. So ML would be -2, -1, 0, 1, 2. ML tells you which one they're in. And F orbitals are when L equals 3. And remember, you can only have 4f and 5f, so you have to be in the 4th energy level or above. And there's 7 different f orbitals. So -3, -2, -1, 0, 1, 2, and 3. And that tells you which ones the electrons are in. And remember that as you get farther from the nucleus, the energy increases. Now, the last type of quantum number is the electron spin. So electrons spin on an axis, and the spin magnetic quantum number, or MS, can either be +1/2 or -1/2, because remember, electrons have to be different ways, one up, one down. That's because they spin different ways. If they spun the same way, then they would repel. So here's just an example of quantum numbers, and we're actually going to go over this in class, so this will make a lot more sense. Remember that the Pauli exclusion principle says that no 2 electrons can have the same set of 4 quantum numbers. So no 2 electrons can have the exact same set of quantum numbers. So each electron is identified by its quantum numbers. So for two electrons to be in the same orbital, one must be spin up and one must be spin down. Electron configurations. Remember, electrons are filled in order of increasing energy. And the electron configuration shows the way that electrons are distributed among the orbitals of an atom. Orbital diagrams are using the boxes like the Hogg Hilton. So if they ask you for an orbital diagram, it means you have to draw out all the boxes. Hund's rule, so that it says that unpaired electrons always have spins up, and that electrons each enter their own separate orbital before they pair up. And this is because that minimizes electron pair repulsions. Remember, all electrons are negative, so if they each have their own orbital before they pair, there's less electron-electron repulsion, meaning the negatives don't repel the negatives as much. The shortcut method is another name for condensed electron configurations, and we'll review this in class. And some important exceptions. For transition metals, remember 3D always fills after 4s, same with 4D and 5D. In the lanthanides and actinides, the 4Fs and the 5Ds are very close in energy. Okay, and so actually some lanthanides have 5D electrons, and we'll talk about that a little bit more. For example, lanthanum, even though it's located in the lanthanides, actually has a 5D electron. So that's an exception. Okay. In the actinides, uranium and plutonium are the best known. These are the 5F electrons. They're radioactive and they're not usually found in nature. Remember, when counting valence electrons, D and F electrons are not considered valence electrons. And some important exceptions to electron configurations. Okay, usually chromium, you would think, has 2 4s electrons and then the 3ds fill. Well, actually chromium only has 1 4s electron and 5 3d electrons, and the same thing with copper. Copper only has 1 4s electron and 10 3d electrons. So we actually lie to you in Gen Chem, and those are exceptions to the electron configuration rules. Lastly, paramagnetic versus diamagnetic. Paramagnetic atoms are atoms that have unpaired electrons, and they're paramagnetic because they can be attracted by magnetic fields. Diamagnetic atoms have no unpaired electrons, and they're actually repelled by magnetic fields.